Okay, so we were trying to get a formula for the number of non-intersecting lattice paths uh, associated to TSSCPPs. So remember what the formulation was. So we had starting points which were on this line, which is whatever, y equals 1 minus 2x or something, whose coordinates are 2 minus 2i, I minus 1. And the ending points are free but lie on the line y equals 1 minus x. And so we had the starting points indexed from 0 to n minus 1, and we had given additional structure which was the matching. So which was a matching of the starting points. And remember that we said that the number of starting points, or the starting points, are indexed from 1 to n minus 1 if n is odd, and 0 to n minus 1 if n is even, so that the number of starting points is an even integer. And this we could do because S naught is the trivial path, starts and ends at the same point. And the point of doing this was to add the structure of matching the starting points. And I remind you that Tn is the set of all paths, matching or intersecting or not, common end points or whatever. No restriction. All upright paths. And we let n bar be n if n is even and n minus 1 if n is odd, so that n bar is even. And it is precisely the number of starting points. So what we had done was to add this matching pi on the starting points, and we defined the inversion number of a pair of lattice path, family of lattice paths, that is L1 to Ln bar, and pi, which is the number of pairs of starting points I and j, such that the ending points are switched, so they are in the wrong order. So it's just like an inversion number of a permutation, but we only focus on pairs ij and pi. So there are exactly n bar by 2 such pairs, and we only care about them. And the weight of such a pair, family of NILPs and this matching, is 0 if any two endpoints are equal, and is otherwise minus 1 to the number of inversions. Okay, and the weight of a given family of lattice paths is the sum over the sign of matchings of the sign of the matching times the weight, and the sign of the matching, remember, is the number of crossings. So we did this example with one crossing and of size 4, so that there are 3 matchings, and for each matching we computed the inversion number and hence the weight, and we computed the sum of the weights by also involving the sign of the matching. Okay, and the lemma that we are going to prove now is that the number of non-intersecting lattice paths is given by this sum of these weights over all lattice paths. Okay, that's what I'm going to prove now. So I have rewritten this lemma. So what it says is that even though there are many more paths than non-intersecting ones in Tn, if I sum over all the weights, I will get only contributions from non-intersecting ones. Okay, so let me go towards the proof. So it will suffice to prove two things. A is that the weight of a lattice path is 1. A family, I mean, weight of family of lattice paths is 1 if L is a non-intersecting family. So if L is an NILP, then its weight will be 1. So it will contribute with the weight with 1 over here. And B, the sum over WL is 0 over all intersecting L's. So if I can show this, I'm done, because then this sum from B, the contribution only comes from non-intersecting lattice paths, and from A, each of them contributes 1, so you get 1. Okay, so I hope that's okay. Now let's prove A. This is the easier part. So if L is an NILP, then it is clear that W of L comma pi is 1 for all pi in an interval. Why? Because let's go back. So what is W of L pi? It's well, it's 0 if any endpoints match, but that's not the case because L is an NILP. It's minus 1 to the number of inversions, where this is the inversion definition. But for any pair ij, they do not get switched, right? So no matter what pi you take, the number of such pairs is going to be 0, because the number of such pairs, number of any pair ij, any such pair ij is 0. Okay, any such pairs ij's, right? So this part is obvious. Therefore, the sum over pi in mn bar W of L pi this way, W of L sine of pi. This guy is always 1, so this is the sum over pi in mn bar of just the sine of pi. Okay, so what we are doing is simply summing the sine of a matching over all matchings, and by definition of the Pfaffian, this is just equal to the Pfaffian of the matrix, which is zeros on the diagonal, and that's always true, plus 1 on the above the diagonal and minus 1 below the diagonal. So every single entry over here is plus 1, and every single entry over here is minus 1, right? Because remember, the Pfaffian is the sum over matchings of the sine of the matching times the product of the entries above the diagonal. But if every single entry above the diagonal is 1, this product always gives 1. So this is what this is. And I leave it for you as an exercise. Actually, I have given it in the homework. So this is an exercise to prove that this is always plus 1. Well, notice that this is not unreasonable, because the number of matchings is always an odd number. So what this is saying is that the odds dominate the, the sign is plus 1 more time than it is minus. Okay. So yeah, so I've left it as an exercise. I don't remember if that was to be submitted or not, but there it is. So this guarantees the first part. So weight of any non-intersecting lattice path family is +1. Okay, so that takes care of the first part. Now I want to show that if I sum over all intersecting lattice paths of the weight, I'll get 0. But here, so the idea is similar to the proof of the LGV theorem, lemma, whatever. So for every intersecting L and every pi in Mn bar, we will construct another pair L prime M prime with opposite sign, with opposite weights. Okay, so this will give a sign reversing involution, which will cancel all this stuff. So this was the idea of the proof of the LGV lemma, and that's what we're going to do here. And okay, so suppose L is such an intersecting NILP. So choose, so among all intersection points, of L, we'll choose those closest to one of the starting points, and among those choose the one with largest x coordinate. This is just to fix, that is to say, it's closest to the origin. And this is just to fix some convention. It's not really important what you do. It's just some convention that fixes these guys. But what is the point of this choice is that then necessarily two consecutive paths Li and Li plus 1 will intersect. Okay, because you are choosing them closest to the starting point. Right? So you're choosing them closest to this line. So then if two faraway guys intersect, then you will find something closer that intersects and so on. And as I said, the second condition says that we are closest to the origin. Largest x coordinate. Right? So that's what it is. Okay. Now, so now if endpoint of some if endpoint of Li equals endpoint of Li plus 1, then the weight of L is the sum over pi weight of L pi sine of pi. But what is the weight of such a L of pi? If this happens, then this weight is necessarily 0, right? For all such pi, right? So this first part does not involve pi. So this guy is 0, and so I get a big fat 0. Okay, so we don't need to worry about this case. If not, we create L prime as in the proof of LGB lemma, as in the proof of the LGB lemma, by exchanging the paths of Li and Li plus 1 after the intersection. Okay, that is one part. And so what are we doing? So another color. So let me use the same color as over here. So yeah, so I use that. Okay, so here is sorry. So here is I, here is I plus 1. So this is EI, and oh, maybe I should use some other color. EI plus 1, and what we are doing is we are going to switch these guys. Okay, so now let me do it really carefully. So I plus 1 starts like so, and then goes like that to E prime I, which is E prime I plus 1, which is EI, and Li goes like so and goes here and gives me E prime I, which is E I plus 1. Okay, so this is Li, L prime I, L I plus 1, L prime plus 1. Okay, so that gives me L prime. Moreover, remember we have to change pi also. Moreover, change pi to pi plus 1 by exchanging I and I plus 1. Okay, so wherever I was connected, you put, whatever I was connected to, you connect it to I plus 1 and vice versa. Okay, so, oh sorry, what did I write? This makes sense. Pi prime, sorry. Right, so this is the new matching. So remember what, so this is our new lattice path L prime and our new matching pi prime. Okay, so we claim now that W of L pi sine of pi is minus W of L prime pi prime sine of L. Okay, so we want to do that now, but there are two cases. Depending on the on whether I is matched to I prime in pi or not. So okay, so the first case, I already used I above, so let's say 1. If this is case B, remember, this is part B, sorry, of the proof. So if I and I prime, I plus 1 are not matched in pi, then we have a situation like so. Okay, so let me just copy this figure and add some more structure to it. Give myself some more room. Okay, yeah, realize this. Okay, so let's suppose that I plus 1 is matched to some k and I is matched to some j. So here is k and it goes like so, whatever, to ek, and I plus I is matched to some j and it goes whatever and it comes here to some ej. Oh, I am running out of space here actually. Okay. Let me try to squeeze this in. Okay, so over here, now you see, so I still have k, but k is now matched to I, so I'm using this color. So that is E prime k, but that is ek itself because nothing happened to that. And here j is now going to be matched to I plus 1, so I'm coloring it in blue. And here I have E prime j, which is also ej. Okay, and maybe I'll draw this separator so that there's no confusion, and we're going from it. Okay, and what was the matching now? The new matching is like so. So don't worry so much that I have put k on this side and j on this side. I mean, anything is allowed. K and j can both be on the same side, arranged in either order, or they can be on the other opposite direction. The argument is not going to change. Okay, but let us see what happens now. Okay. So what happens to the number of crossings? So okay, so two things are happening. So this is pi, and this is pi prime. Okay. So pi has changed, and L has also changed. Li and Li prime have changed, right? So two things have happened. Then the number of crossings of pi, what is the relationship between the number of crossings and the number of crossings of pi prime? Anybody? In general, I mean, don't just think about this figure. But in general, no matter where k and j are, what can you say about the relationship between chi and the chi of pi? Chi of pi, remember, is the number of crossings in pi. So what's the relationship between chi of pi and chi of pi prime?
I think it will change by 1.
That's right. That's right. You said that. Yes, Upaman is exactly right. So they will change exactly by 1, either plus or minus. So for example, if k were this side and j were the other side, then they would untangle. Here they get tangled. But if you look, even when k and j are in the same side, for example, if j were here in between k and I plus 1, for instance, then here they would have one extra crossing, and here they would have one less. You know, so like that. You can easily see that this is the case. So that implies that the sign of pi prime is minus sign of pi. The parity changes. That's the key point. Okay, that's good. Now we also want to compare the weight of L pi and weight of L prime pi. So what has changed now? So notice that here we would, so remember that the weight is minus 1 to the number of inversions, and the inversions are the number of pairs which are off sequence in pi. So here we would compare k with I plus 1. So we would compare ek with ei plus 1. And here we would compare e prime k with e prime I. But e prime I is exactly ei plus 1. So here you are comparing ek with ei plus 1. Here you are comparing e prime k with e prime I, which is the same, which is again ek with ei plus 1. So the comparison does not change for k. Similarly, for j, you are comparing ei with ej. Now you are comparing e prime I plus 1 with e prime j, but that is the same as comparing ei with ej. So that does not change. Okay, so that's really the key, one of the key ideas here. So this is why the matching aspect is so useful. We were comparing. We were comparing ek to ei plus 1 to compute W of L pi, and now we are comparing e prime k to e prime I to compute W L prime pi prime, but e prime k is ek and e prime I is exactly ei plus 1. So the in does not change. Maybe I'll write that later. Similar argument holds for ej and ei. Thus, and all others are unchanged. No other matching is changed. No other lattice path is changed. So the contribution of the inversion for any other guy is the same. So or I can write it directly, W of L pi is equal to W of L prime pi. It did not change. So that means the product changed by a sign, because the sign is what contributed to the change. Okay, so we have proved this claim in the first case. In the second case, which was if I and I plus 1 are indeed matched in pi, then pi prime is pi. Right? So no change. So sine of pi prime is sine of pi. Right? And now let me put back the figure. So here it were in pi and here they are in pi prime. So here the sign does not change, sign of pi does not change. What about the weight of L pi? But the intersection points EI and EI plus 1 have now switched. I mean, remember that we are just looking at the first intersection point. I mean, they could have many more intersections later. But no matter what it is, if there was one extra inversion here, there would be one less inversion here and vice versa. And so we get an extra contribution, an extra or less contribution to in pi L pi, sorry. Thus, W of L pi is minus W of L prime by pi. Right? So, in the first case, the matching is what contributed to the sign. In the second case, the path is what contributed. The NILP is what contributed. So it's really beautifully organized, and you know, in each case, we get this cancellation, and thus the total contribution to all intersecting paths of all intersecting paths to W of L is 0. So this proves part B, and we are done. Right? So remember, part B was proving that the sum over weighted lattice paths, weight of intersecting lattice paths is 0. Part A we have done modulo this exercise. Okay, so we have proved, and rather it's rather elegant proof using non-intersecting lattice paths and matching. So this was the new idea of Stembridge, which allowed him to compute. Well, we are not there yet, but this is the key lemma. This is the analog of the LGB lemma for non-intersecting lattice paths, where the endpoints are free. Starting points are fixed, endpoints are free. One can generalize this to also include starting points which are free. Okay, and Stembridge does this in full detail in a really beautiful paper. Okay, so any questions about the proof? Okay, so we have shown that the number of TSSCPPs in a 2n by 2n by 2n box is equal to the sum over all families of lattice paths in Tn of W of L. That's what our lemma said. And now rewriting it, I have I will interchange the sum. So I'll first sum over pi in mn bar. Then I'll write sine of pi. And I'll write sum over L in Tn of Wn. Okay. So the aim now is to express this as a Pfaffian, and you can see that the starting point is correct. So if I can express this as a product of entries of some matrix appropriately, then I can write it as a Pfaffian. So we want to evaluate this. We now okay. So I remind you that recall that L is L naught up to Ln minus 1 if n is odd. I'm sorry. L is even. I want an even number. No, sorry, that is correct. Because no, these are n total paths, so this should be n. And L1 up to Ln minus 1 if n is odd, because this is n minus 1 to paths. Yeah, sorry, it confused me. Let's take my notes. Okay, so now let's look carefully at what this is. Okay, so consider the path Li. Which starts at Si, which is 2 minus 2i, I minus 1. Okay, so here is Si, which is whatever I just said, 2 minus 2i, I minus 1. Here, okay, here is the line y equals 1 minus x. And okay, so what are the possible ending points? So it can only take up and right steps. So let's look at this coordinate. So what is that? It has x coordinate 2 minus 2i and y coordinate is 1 minus x. So it's 1 minus 2 minus 2i. So that's 2i minus 1. And this point has y coordinate I minus 1. So x coordinate is 1 minus y. That's next, sorry. So 1 minus I minus 1 is 2 minus. So this is 2 minus I minus 1. Right? So possible ending points. For Li are in the set 2 minus r, r minus 1. That's the general way we have indexed the points here. Where, I'm sorry, where what is the minimum value of the y coordinate? So I minus 1. So r is at least as big as I and at most as big as 2. Okay. So the number of possible paths ending, so I'll call this let's say a generic point here, I'll call ER, which is 2 minus R minus 1, ending at ER is what is, I mean, it's a binomial coefficient. So you start here, you take some steps and you reach there. So you want to see how many total horizontal steps are there, how many total vertical steps are there, and you take the appropriate binomial coefficient. So this is equal to how many, so let's compare. So how many horizontal steps are there? So that's 2 minus R minus 2 minus 2I plus how many vertical steps are there? R minus 1 minus I minus 1. Choose just let's say a number of vertical paths. So R minus 1 minus I minus 1. Let's start to cancel. So there will be a lot of cancellations. So this one cancels this one. This 2 cancels this 2. This minus R cancels this plus R. Right? So at the end you have plus 2I minus I, which is I. And here you have the same one is cancelling. So this is I choose R minus I. Right? So this makes sense because if R is smaller than I, you will get something negative, and so the binomial coefficient will be 0. And if R is greater than 2I, then 2I minus I is greater than I, and so you will have something where the lower index is larger than the upper index, and so that binomial coefficient will also 0. Okay? Okay, so this is the number of paths ending at ER. Okay. Okay, but we want, remember, we want to evaluate this. So this involves pi. So we want to account for the weight of such a thing where we consider pairs of lattice paths. So now we also take pi into consideration, right? So suppose ij belongs to pi. Let's see what happens there. And the ending points for Li and Lj are E sub R and E sub S, respectively. Oh, E sub S, let's say, not respectively, let's just see what happens. So E sub R, remember, is my notation for this. So ES is 2 minus S. So let's write that. Okay, so is that so? Here is SI, here is SJ, and here is my pi matching these two, and so let me draw the line first. So that's the line. So right. So So this is, let's say, ER and this is ES. Okay. And we will assume here that R is less than S. Okay, so R, we will always take ER to be ending, to be below and right of this. Okay, so now so this is the first case, if Li ends at ER, so here also I should have said I is less than 0. Okay, so Si is before this. So if Li ends at ER and Lj ends at ES, okay, then how many ways are there? Then the number of such paths is what? Is just the product of the binomial coefficients. You take all possible lattice paths going from Si to ER and from Sj to Es. So for each of them we have this formula. So this will give I choose R minus I, J choose S minus J. And this will automatically take care of the fact that ES should not wander away too far from Sj, that is, it shouldn't go too far left or too far below, and similarly this is automatically going to take care of it. Okay. Note that we are not imposing any non-intersecting business. We are taking this sum. Okay, and that's involved over here. Okay, this is if so again two cases. Let me just say that to be. So this is the first one. The second case, again, use the power of my tablet. The second case is when they go the other way. Okay, so okay, now if Li goes to ES, sorry, and Lj goes to ER, then the number of such paths is what? Now it will be the other way around. So I choose S minus I and J choose R minus J, okay, because of the way the paths are going. But all such paths in the weight will come with a positive sign. So all such paths, whether they intersect or not, contribute plus to WL pi, and similarly all such paths, these will of course necessarily intersect, all such paths contribute -1 to WL pi. So right, so is that clear? So the total contribution for this pair ij, ij is what? Is I choose r minus I, j choose s minus j, minus I choose s minus I, j choose r minus j. Okay. We have assumed I is less than j, and it may not be immediately obvious to you, but you should be able to convince yourself that this fellow is non-negative if r is less than j, right? Which is what we have assumed. I is less than j, r is less. Okay, but we have to do this now for each pair. So we have to include this contribution for each pair ij and pi, and so our desired sum, which is what we wanted to evaluate, remember, this fellow. So the sum over L in Tn Wl pi is equal to the product over ij in pi, I less than j, sum over what? So maybe I should have said it. Okay, but it'll okay. Let me explain this. So I is less than or equal to r is less than s is less than or equal to 2j of this fellow. I choose r minus I, j choose s minus j, minus I choose s minus I, j choose r minus j. Okay, let's. So I hope if that's not clear, look at ER. ER cannot go below SI. So that means R has to be at least I. That's this lower inequality. And S cannot go higher than J. The x coordinate of ES cannot be to the left of that of J. So that means the second inequality comes into play. And so S is less than or equal to 2J. And R is less than S by assumption. So R is greater than or equal to I, S is less than or equal to 2J, and R is less than S. So this is the sum. Okay. So if I call this double sum, if I call it Hij, this is equal to the product over Ij and pi I less than j of Hij. And so we have expressed this sum in terms of a product of things which purely involve pairs Ij. Overall, I mean pairs Ij belonging to pi. Right? So we have what we have shown. We have proved the following theorem due to Andrews. Number of TSSCPPs in a 2n by 2n by 2n box is equal to the sum over pi in mn bar sine of pi product over ij in pi, I less than j, hij, which is equal to the Pfaffian of hij. This is just definition of ij going up to n minus 1, either 0 or 1 less than or equal to this, depending on whether n is odd. Okay. So let me show you this on Sage. So I wrote a program to compute these HIJs, which is just the sum of, so this is binomial I r minus I, js minus j, minus the other way around. R and S are in the same range. I used exactly the same notation as in the notes. And I've called this Andrews Pfaffian, which defines this matrix, and I've used, so if n is even, then it's an n by n matrix. It's naturally indexed from 0 to n minus 1 by Sage's convention. And I use this lambda notation to say it's hij, this hij, if I is less than or equal to j, otherwise it's minus hji. This is just to make sure it's symmetric. Notice if I is equal to j, this is automatically 0, as it should be. And if n is odd, then it's an n minus 1 by n minus 1 matrix, but now it's indexed from 1 to n minus 1, so I have to shift I and j by 1, which I do here. Okay, so let's see. So if I take the Andrews Pfaffian of size 2, its Pfaffian is clearly 2. I take the square root of the determinant. If I take 3, then again it's a 2 by 2 matrix. Again it's 7. So the first non-trivial case is 4. And we should get 42 over here. And we do. Next is 429. Again a 4 by 4 matrix. And that works. I can do one more. So now it's a 6 by 6 matrix. And it's on 4 by 6. And just to show you the structure of the entries, let me take a large enough matrix. So notice that the first row is purely powers of 2, consecutive powers of 2. The next is also powers of 2 after the 4th column. The next row you again get powers of 2, but after the 6th column. And similarly 8th column, 10th column, and so on. Okay? And so they start to differ closer to the diagonal, but far away from the diagonal they are powers of 2. So this I'm going to leave for you as an exercise. It's not in the homeworks, but oh sorry, wrong sheet. Okay, so here's the exercise. Show that. So hij here is a double sum. Right, it's a sum over 2 things, so it's quite a horrible looking expression. And as it is, it's not easy to see how to do anything with it. But one simplification is to reduce it to a single sum. So you can write hij as a sum going from r of r going from 2I minus j plus 1 to 2j minus I of I plus j choose r for I less than or equal to j, which is what we are interested in. And notice that this should be interpreted appropriately. So if r is greater than I plus j, then this is 0, and if r is less than 0, then this is also 0. And from this, if j is greater than or equal to 2i plus 1, then what happens? Then this sum starts below 0. Hij is the sum r from something below 0, but I don't care to take those terms because they are 0 anyway. This is always issues are. And the upper limit is if you substitute, you will find that you do not go more than 3i plus 1. More than I plus j. So you can check. You get this, and so you get actually 2 to the I plus j. So this is this explanation of this powers of 2 business that I just showed you on Sage. Okay. So if you prove this, you'll be able to prove this. So hint for a hint, this is from Rasul's book. So he has given some hints on how to prove this. Okay. All right. Any questions? Oh, yeah. So I want to say a little bit about the proof. So idea of proof. So you see that the entries are quite complicated. So evaluating the Pfaffian is more or less evaluating the determinant. But the entries are highly complicated, binomial sums, and it's not easy to prove. And Andrews is able to do it, but the details are, in his own words, inordinately complicated. So it's not particularly illustrative, but the key idea is a really beautiful idea. Very simple, which is to find a matrix R such that this matrix, if I call it H, such that H times R is lower triangular. I think I should have said, I think I want to say lower triangular. No, upper triangular. So find an upper triangular matrix R such that HR is lower triangular. So then determinant, if you know, then knowing determinant of HR, H times R, and determinant of R completes. This is a very high level and simple idea, but constructing this R and computing actually its determinant is a highly technical exercise, and I think one needed someone of Andrew's technical skill to be able to do it. Okay. So he proved the TSSCPP conjecture using these ideas. Okay. So any questions? Okay. So right. So this completes the proof of the enumeration of TSSCPPs. Not really, because we have hidden a large part over here in this. Okay, sorry. This is not the idea of this. This is so proof of TSSCPP theorem. This is in the same book. So we have proved this part, right? We have proved that it's a Pfaffian. What is left is to evaluate this beast, and this was also in that paper, and as I said, very complicated. Okay, so now I want to move towards the proofs of the Ascent theorem. Again, not able to go through all the details, but at least the broad picture we will be able to state. So we have so far written down determinantal expressions for two of the major players in the story, that is descending plane partitions and totally symmetric self-complementary plane partitions. And so for both of them, the answers turn out to be the same. But remember that the determinants came from very different considerations. So for descending plane partitions, we had, okay, so maybe I should write this. So we have now proved or stated determinantal or let's say lattice NILP formulas NILP results, let's say, for two of the three major players in the story. So for descending plane partitions, we obtained NILPs summed over many possible starting and ending points. That is, you could have either the empty NILP or a single NILP or two pairs and so on, three and triples and so on, and we got determinants of the form identity plus some matrix. So we remember we had delta ij plus some binomial coefficient. And for TSSCPPs, we obtained NILPs with fixed starting and variable ending points. And we got Pfaffian. Somewhat miraculously, we got Pfaffians. Right. So these came from very different considerations, and we got the same answer. Okay. And okay. So for the third case, we now want to prove enumeration formulas to prove enumeration function formulas for ASMs. Right, the last major player, and I think this will take the rest of the course. Okay, so we first, so I will first describe Zeilberger's proof idea. Okay, so to describe that, let me go back to TSSCPPs. So the construction that I'm going to describe now is already due to Mills, Robinson, Ramsey. This approach. We will first encode TSSCPPs in another way. So for this proof, remember what we did. We took slices over here, shells, and we made them into kind of shifted plain partition, strict shifted plain partition with odd integers, satisfying some condition, blah blah. But you might have noticed already over here that when we constructed the slices, we had this extra symmetry. So instead of taking this whole thing, this whole shell, I could have taken the right half of the shell. I could have drawn a line down here, and I could have taken this and this and this and this instead. That would contain all the information of the shell, right? The reason for doing this was to be able to write it as odd hooks, odd distinct partitions, which was why one did it that way. But there's another way of doing it, which is what I'll describe right now. Okay, so let me again copy. Oh, sorry. Okay. Copy the same figure. Okay, so strictly speaking, all the information about the TSSCPP, about any TSSCPP, is encoded in 1/12 of its diagram, of its matrix or table, of its array. So let me show you how. So you take, so what we're going to do is essentially take 1/2 of that figure. So I should have gone up to here. Okay, let me do this first. Okay. So this part over here encodes all this information, because by reflection we'll get this part and then. So what we are going to do, so as shown in the figure. Okay, so what we're going to do is we will encode the heights of cells in that region. So this is 1/12 because there are 6 sides, and so 1/6 would have been up to here, and this or up to here, and this is off in that region. And yeah, so in this example, for n equals 5, we have what? So when I say heights, I don't mean the height up to the bottom, because that's a bit redundant. The heights inside the n by n by n box. So this part is contained inside an n by n by n box. So only the height inside that. So let me tabulate it like so. Okay, so we have, and please tell me if this is not clear. So the first row is all 5s. The second row is again all 5s. But the first cell of the second row is adjacent to the second cell of the first row. So I will start in the shifted array. So 5, 5, 5, 5, right? That's that array. I'm including the diagonal, remember. This one is 5, 5, 4, and I will start it shifted. Okay, now this one drops drastically. So this is this was 5. So this starts with 3, 3 and 2, and the last one. Okay, is that clear? No. Okay, so now we will perform the following transformations to get it into a way that I like to encode it. I mean, there are many equivalent ways of encoding it. So let me do it my way. So we will now subtract every entry from 6, which is n plus 1 in general, and rotate the array counterclockwise by 2 to get an array of the form. So we'll get the following array. So let me keep it here. So we will first subtract every entry from 1, and now then we will rotate. So I'll write the first row starting right to left as a column. So the first row will become the first column. So I will get 1, 1, 1, 1, 1. That is, I read from here to here. It's ambiguous right now, but you'll see. The second row is also becomes the second column of all 1s. 1, 1, 1, 1. Now something non-trivial happens. So here I'll get 2, 1, 1. So I'll read it from top to bottom. Here I'll get 4, 3. And the last one is okay, is that clear? So I warn you, so just remark, the rows are opposite in order compared to Bressoud's convention. So Bressoud has constructed it in exactly the reverse order. So the first row for him is 1, the topmost row for him is 1, second is 1, 1, third is 1, 1, 1, and so on. Okay, so this is just a warning if you're reading the paper. Also, he constructs the array in a very different way. So what he does is to take this this shifted plane partition and rearrange it in some way and does some jugglery and gets this. But I find this a much more natural way of thinking about it. Okay, so the first part is a warning if you are reading the book, and the second is you might want to look at his construction to compare. I mean, ultimately they are the same, but I find this way of thinking about it much more natural. Okay, so such arrays. So let me now define. So let me say what properties such arrays will satisfy. So they will they'll be increasing. So this array is, so let's say the entries are increasing weekly from left to right, and entries are decreasing from top to bottom. And the other funny convention, which is what makes the whole business a bit hard to analyze, is that the jth column is less than or equal to j. So the entries in the jth column, the first column are less than or equal to 1, second column less than or equal to 2, third column less than or equal to 3, less than or equal to 4, less than or equal to 5. So notice that all the entries are going to be positive integers. So the first column is both greater than or equal to 1 and less than or equal to 1. So the first column is actually forced. And this corresponds to the fact that the top row over here is forced. Okay. So let me give the formal definition. So I'm using the terminology due to Zeilberger, but this was defined by Mills-Robinson. So a magog triangle of order n is an array of the form Mij. I'm using M for magog, where I goes from 1 to n and j goes from 1 to n minus I plus 1. So that there are n entries in the first row all the way up to 1 entry in the last row. Okay, where three properties are satisfied. One is less than or equal to Mij is less than or equal to j. That's the column condition I mentioned. Mij is greater than or equal to mi plus 1j. So this is a decrease along peak, decrease along columns. And the last is Mij is less than or equal to Mij plus 1, which is weak increase along rows. Okay. All right. So why the name? So this is half the name. So there were. So the name is biblical. So there were two sort of warring tribes in the Bible. They were called the Gog and the Magog. So this is Zeilberger's terminology. So he calls these Magog triangles, and he calls what we defined earlier as monotone triangles, he calls them Gog triangles. Okay, so very, I don't know, it's a kind of strange name for these guys because it comes out of nowhere, but somehow the name seems to have stuck. Maybe partly because he proved the connection. Okay, so let me give you, or maybe it's a good time to stop. I will show you in the next class how these are kind of classificatory by looking at the Magog triangles of order 3, and you'll see that they are exactly 7 of those. Okay, so maybe I'll run this. Yeah, okay. So I'll stop here. I think it's a good time to stop.